And now we're heading toward example 5. Okay, to figure out how many turns a polynomial function makes, or how many turning points there are in the function, you just determine what the degree is, and then you subtract 1. So say the polynomial is, I don't know, let's say f of x equals x squared minus 1. Okay, the degree here is degree 2, so the number of turns, 2 minus 1, is 1. And of course it's a parabola, so yeah, that just makes 1 turn. Let's say we have a function f of x equals x to the third power plus 3. Well, we see the degree is 3, so to determine the number of turning points, 3 minus 1, it's 2. So that function, that graph, would make 2 turns. Okay, so all 4 examples prior to this have led up to this time where we talk about a strategy for graphing polynomial functions. First, you want to use your leading coefficient test to decide, what it looks like on the left side and the right side. And next, you want to find the x-intercepts by setting the function equal to 0. Once you find those x-intercepts, or we also call those the roots, you look to see like how many times those roots are used as an exponent, or we're finding the multiplicity. So if the multiplicity is an even number, then the graph just touches the x-axis at that root and turns around. If that multiplicity is an odd number, then the graph's going to cross the x-axis at that root, at that x-intercept. And as long as the multiplicity is greater than 1, the graph is sort of going to flatten out near the root on the x-axis. Okay, so that's just the second step. Step 3, figure out what the y-intercept is by finding f of 0. In other words, substitute in 0 for x. The fourth step, use what you know about symmetry to help you draw the graph. And then finally, to figure out how many turns it makes, you take the degree, you subtract 1, and that gives you the number of turns. Okay, so example 5, we're going to try to go through all 5 steps and graph a polynomial function. Step 1, you want to determine the end behavior. Remember, we need to use the lead coefficient test. The lead coefficient here is 2, and the degree of the polynomial. You may be like, wait a minute, what do you mean it's degree 3? Well, this is degree 2, right? But this is also degree 1. And so if you'd multiply this out, you're going to end up with an x squared. And this will end up with an x in it. So x squared times x, you'll end up with an x cubed. There's no need in really multiplying the whole thing out because no other exponent will be larger. So that's how you realize it's really a third degree polynomial. Since the degree 3 is an odd number and the leading coefficient is a 2, it's a positive number, that means if you go back in your notes to your chart, the graph is going to be up on the right-hand side and down on the left-hand side. Okay, so we're going to use step 2 to find the x-intercepts, or the zeros of the function, or we can call those roots also. Thank goodness this is really sort of already factored. So we've got 2 times the quantity x plus 2 squared times x minus 3 equals 0. So first let's solve this part. X plus 2 squared equals 0. Well, to undo a square, we take the square root of both sides, and so that's x plus 2 equals 0. subtract 2 from both sides, x is negative 2. That's one of the roots. Now we also need to solve x minus 3 equals 0. So if x minus 3 equals 0, add 3 to both sides, x is 3. So x equals negative 2. Whoops, negative 2. Now that had a multiplicity of 2, and x equals 3. That just had a multiplicity of 1. Okay, so those x-intercepts we found x equals negative 2, and it's a 0 of multiplicity 2. Now, if the multiplicity is an even number, means the graph just touches the x-axis at x equals negative 2. It's going to flatten out and turn around. Our 0 of x equals 3, that has a multiplicity of 1. If the multiplicity is an odd number, it means the graph crosses the x-axis at x equals 3. And you can take a look at what that looks like in the sketch over here. Okay, now step 3 to find the y-intercept. So we substitute in a 0 for x. And so f of 0, that's 2 times the quantity 0 plus 2, well that's just going to be 2 squared, and times 0 minus 3, well that's just negative 3. And so let's see, that's going to equal 2 times 4 times negative 3. And let's see, isn't that negative 24? I do believe. So the graph passes through the y-axis at 0, negative 24. And that's pictured right about there. And now we've also determined, remember, in a previous step, it's down on the left-hand side of the graph, it's up on the right-hand side. We just talked about how it makes a turn at x equals negative 2, and you cross the x-axis at x equals 3. So see, our graph is starting to come together. We're not sure exactly how it looks totally, but it's starting to come together. We also may want to go ahead and figure out what the function does at x equals 1 and x equals 2 to get a final idea of what the graph looks like. Okay, so as we just said in step 3, the y-intercept is negative 24. That means the graph passes through the y-axis at the point 0, negative 24. And to figure out, what the rest of this is going to look like, let's figure out what f of x is at x equals 1 and at x equals 2. So let's see, f of 1, that's going to be 2 times 1 plus 2 is what, 3 squared times 1 minus 3 is negative 2. Let's see, that's 2 times 9 times negative 2. And so I guess that's what, negative 36. So when x is 1, y is negative 36. Now let's take a look at f of 2. So let's see, that's going to be 2 times, okay, x is 2. 2 plus 2, that's 4 squared, times 2 minus 3 is negative 1. So that's 2 times 16 times negative 1, and that's what, negative 32. So on our function, when x is 2, y is negative 32. Okay, so we're getting closer to have a complete graph. Step 4, use some possible symmetry to draw the graph. Well, we realize right away it is not symmetric about the y-axis. And to be symmetric about the origin, remember, if you rotated it 180 degrees around the origin, it would map onto itself. That is obviously not the case here. So we don't have symmetry about the origin either. So, symmetry isn't going to help us any. We'd already taken care of this part of the function, the end behavior, in step 1, and we realized we had some intercepts, x-intercepts I should say, and we had a y-intercept. We knew that because the multiplicity was even on this root, that it made a turn. Since the multiplicity was odd right here for this root, you went from one side of the x-axis to the other. And then, of course, to complete the graph, we figured out f of 1, f of 2 to take care of this portion. And even though we've gone ahead and graphed, let's just, step 5, use the fact, to figure what the turning points are. The degree of the polynomial was 3. So to figure out the number of turns, n minus 1, 3 minus 1 is 2. And if you check, we've got one turn here and a second turn here. So that does certainly check out.